record on this computer. Okay. As soon as I'm done, I'm going to get all the lectures of the week up today. Okay, so we are already in lecture number 20. Wow, semester went fast. We were talking about electron spin. So this is a property of a particle of an electron that actually can be measured and has some physical consequence. We have the thing that the electron can have an intrinsic angular momentum, and if it has an intrinsic angular momentum, anything that has charge and has angular momentum has magnetic moment. Okay, so that's sort of the thumb rule. If something is linked to something that is rotating, as an angular momentum does, so we have orbital angular momentum, we have a magnetic moment associated with the orbital angular momentum, we have an intrinsic angular momentum with the spin of the electron, so we have an intrinsic magnetic moment, and in the presence of a magnetic field, that thing has influence in both cases. And this was the original experiment performed by, this is the Stern-Gerlach experiment, these guys that actually measured that the thing actually had this only two trajectories, which is consistent with a particle having an intrinsic angular momentum of spin 1/2, okay, in order to have only two, an even number of displaced curves when the an atomic beam is passed through a magnetic field with a gradient, okay? So you can definitely produce a force on these particles and separate the trajectories if that's the case, okay? So we have this, the picture, the complete picture is we have an angular momentum linked to the particles that is actually quantized in this way. And we have an angular momentum linked to the spin, which is, the spin is in units of h bar. In the case of the electron, the intrinsic angular momentum is plus or minus h bar. This is what we call, this is why we call this a spin 1/2 particle. That's what the electron is. The modulus of the spin is actually measured in the same way as the modulus of the electron. So this would be the case. So somewhere there should be a 1, okay? And the magnetic moment is related to the spin of the particle in this way, where we have this gyromagnetic ratio, which is something that links the magnitude of the intrinsic spin to the magnitude of the intrinsic magnetic moment, okay? So if this part has a magnetic moment, I can actually put a magnetic field, and I will have different energies. So the magnetic moment will have the tendency to be aligned with the magnetic field in the lowest energy configuration, okay? And something similar happens with the orbital magnetic moment, which is the one over here. And since we have an orbital magnetic moment and we have a spin magnetic moment, it makes sense to define a total angular momentum, which is the sum of the orbital magnetic moment plus the spin magnetic moment. And if one looks at this case, when L could be 0, 1, 2, 3, 4, 5, whatever the values of L are possible, the spin magnetic moment has only one possible value, because it's an intrinsic magnetic moment, so it's only a 1/2. So essentially, the total magnetic moment would be with the when the spin is actually aligned, or the total magnetic moment could be aligned or misaligned or counter-aligned with the angular momentum. So if the particle is rotating like this, the angular momentum should be like that, but the spin could be pointing that way, pointing down. Then in that case, the total angular momentum of the complete system will be a 1/2. It means you have to add the 1 in that direction with the 1/2 in the opposite direction, you get a 1/2. And the reverse thing would be that the particle is actually spinning with the angular moment with the spin angular momentum pointing in the same direction as the trajectory of the electron. And in that case, the sum of the spin will be if the orbit is an L equal 1, it will be 1 plus, you know, a half, so it would be 3 halves. So you can have essentially the J will be the magnitude of the L plus or minus a half, okay? For a particle, this is the total angular momentum of an electron in a state with L equal to 1, okay? In this way, an electron in a p state, I have just described, it can have a total angular momentum equal to 3 halves when the orbital and the spin are aligned, or it could be a total angular momentum equals to 1/2. And there's a spectroscopic notation that actually is being used for describing this, which is this thing over here. So you in this position in this superscript, you write 2s plus 1. 2s plus 1 is the number of possible spin states that the system would have. Let's say you have something that has a total spin equals 5. Okay, if you have something that has if the sum of the intrinsic spins is 5 and you have something that is 5, it means that you have 11 possible states, okay, where this thing could be. You know, 2 times 5, 10 plus 1, 11, okay? In the case of spin 1/2, this value, if S is only 1/2, you have only 2 possible values for the spin, up or down. So this is the number that is given here, is the possible number of orientation of the spin, and that is what's labeled as 2s plus 1, okay? The letter in between here, the L, represents the actual orbital angular momentum, and this is a p state because I'm saying this, if it is a p state, I recognize it is a p state, but I have 2 options for the total angular momentum, which is the angular momentum counter-aligned or aligned with the orbital angular momentum, and so you can get for a p state you can get 2p 1/2 and 2p 3/2 states. Okay, so this here is the way to label the states when you are looking at electronic states in a system. Okay, it could be an atom, for example. If we do the following thing, if we describe that a particle like an electron that it has a non-zero a non-zero angular momentum will be rotating around the nucleus with a non-zero angular momentum. It means that the nucleus will be rotating around the electron with a non-zero angular momentum. It means that rotation will induce a magnetic field in the position of the electron, and simply by electrodynamics. Okay, so in graphic terms, it's essentially there is a coupling between the orbital angular momentum and the spin orbital angular momentum mediated by the interaction with the nucleus. Okay, so if that happens, you can have what we call a spin orbit interaction. So the spin and the orbit component of the electron interact and they split. There's a certain energy. There's an L.S factor here, and if we put all of that together, we get the. And there's also a correction that is a relativistic correction that has almost the same magnitude that has to do with this 3/4 that is written here. This because the Schrödinger equation is a non-relativistic equation, but to describe the motion of the electron. But what happens is that when the electrons are very far out, the actual angular momentum, those electrons really have an electronic momentum which is very close to relativistic. It's a fraction of a relativistic momentum of the electron, simply forced by the confinement and the fact that what we will see, the exclusion principle, which makes the energy of the electrons very high. So in the case of the hydrogen atom, we can actually find out that those relativistic corrections are very important, okay? And it can be written like this. And if you incorporate the spin-orbit interaction, it comes through this term here, and these two terms now modifies the total expression that we have for the energy levels of the hydrogen atom. Remember, before the energy expression was given by the first term here. So this term here is some sort of a correction, okay, to this term when we start considering that there is an interaction between the spin and the orbital angular momentum. And this constant that appears here is a constant of the order of 1/137. And this is an adimensional constant. This constant is equal to this number here, and this number here is an I-dimensional constant. So you are dividing many things, and those things that you are dividing, it happens to be just a number, okay? So the spin orbit coupling, this L dot S term, which is what we are seeing reflected here in this expression, somehow removes the degeneracy of the that we were seeing before. Before, anything that has the same value of n, and you can have any values of L and M for the angular momentum, all have the same energy. But now this is not true. This is not true because even though this value here, alpha square, is very small, there is a slight difference between the energy levels. Okay, and this is what I am trying to draw here. I'm trying to describe the fine structure of the hydrogen atom. So the difference between the ground state is n equals 1, L equals 0, and J equals a half, because L is equal to 0. So we're looking to the ground state level here, this state here. If there's no perturbation, meaning if we don't include the spin orbiting interaction, the energies of these two levels will be minus 13.6 and minus 3.4. If we actually use this expression, this expression is not a very simple thing to get. Okay, you really have to do some serious work with work functions and calculated expectation values of operators and things like that in order to get this final expression. Now we are just using the result here and finding out that this state here is actually when I have a state with J equal 1/2, I have only here minus 3.4 electron volts plus this term here. But this term here, you have to be reminded that this term here, alpha square, is of the order of 10 to the minus 4, okay? And so this is a very small correction, what we're seeing. So that's why the previous model is what people mostly know, because it makes very sound predictions of what. But if you want to start looking at things in tiny bit of a detail, you get to see and describe this in the proper way, and you see that some of the degeneracies are lifted, because these numbers here now depends on the value of J. Here, if the J is equal to 1/2, that means that the electron is actually pointing in opposite, the spin of the electron is pointing opposite to the orbital angular momentum. And you can also have the 3/2. And when you use this expression here, and instead of 1/2, you use 3/2, this number here is larger, okay? So if this is larger, it means that this number is smaller, so there's a difference between J1/2 and J3/2. So the orientation of the spin makes a difference in the position of the energy levels, simply because the spin-orbit interaction is something that exists, okay? What I would like to switch now is to the problem of some atoms with many electrons. This is indeed not a very simple problem from the point of view of quantum mechanics, and I'm going to tell you immediately that nobody has solved anything different from the hydrogen atom and quantum mechanically in terms of algebraic solutions, okay? One would say, well, that's not very important. We have computers, we can, get the functions, get everything out, and we can do this numerically. Definitely you can, but it's the thing is the involvement of doing this thing in the proper way. It's difficult. So this is the case of hydrogen. Hydrogen, you get only kinetic energy of the electron plus the potential energy, and then you have to solve this equation. When you multiply this, you change this by the proper operators, and you want to solve this equation and find the eigenvalues of the energy, and this is what we have done. And we know is the eigenvalues are labeled by the quantum number n, and it's approximately equal to minus 13.6 electron volts, should say here. It doesn't say, probably cut it out, divided by n squared. Okay. If we want to think of a problem of an atom with many electrons, then the Hamiltonian or the Schrödinger equation will be a bit different. The H that I have to put here must have all the kinetic energies of all the electrons. Then there's the potential. There's the potential energy of each one of the electrons with the nucleus, okay? And there's also the interaction between electrons, because the electrons are also charged particles, so there's the electrostatic interaction between them. And so you get a very cumbersome form of the potential, okay? Well, this has, if we, let's say this is an atom with Z electrons. So this here should be 3C time derivatives of second order time derivatives associated with each one of the coordinates, okay? And this thing here has the square root of the difference of, well, it gets very cumbersome in terms of the variables involved in the equation, but that's okay. We can always write it down and know what we want to do. We want to solve, to find this solution, which is the energy eigenvalues of a multiple coordinate wave function that depends on the different coordinates of the electrons here. And I somehow operate on that with this Hamiltonian, and then I want to make that equals to the energy times the same wave function. If I solve this thing, I can find the wave functions for the electrons and the energies, which are the eigenvalues. And as I've been telling you, before, I don't know why did I do this. Oh, it's not my fault. Let me see. Okay. So if I do this, I assume now that you know, the complicated thing has to be solved in a certain way. And how do we plan to solve it? The first thing, approximation that we would like to do is ignore the electron-electron interaction. The electron-electron interaction, in all decency, is as strong as the interaction between the nucleus and the electron, okay, that are, you know, going around the nucleus. So why do we neglect the electron-electron interaction then? Simply because it's easier to solve. So this is the approach that physicists have. You know, let's look at this at something simple, something that we can understand, and then we just plug in the real world in a way that we can still solve it or make a sense out of it. So the first naive thing is assume that the electron interactions are negligible, and the electron moves in a potential of positive nucleus of charge CE, okay? So each electron has an energy of the form, this is the form of the electron. Now, if you, no, okay, no. You cannot be reminded of this, but if you, the energy S sub n of the hydrogen atom has an E to the fourth in the expression for the energy, and when you actually evaluate this, you get this 13.6 divided by n squared. But the E to the fourth has two contributions. One of the E squares comes from the charge of the electron, and the other E squared comes from the charge of the nucleus. Since now I'm just saying I'm going to change the charge of the nucleus, I only have to introduce a C squared because the charge of the electron keeps being E squared. Okay, so this is the energy of the energy levels of a nucleus made out of C protons, and only and the energy of the electron and the charge of the electrons are E. So this would be the energy levels of a nucleus built like that. It's almost like a hydrogen atom, but with a nucleus with a higher number of protons on it. Okay. Well, you know, as it says here, this is too drastic an assumption, and you can do it, but it doesn't provide really with meaningful results in terms of how do we understand the system. Yeah. Meaning, we want to compare these things with actual values seen by the energies of particular things. If I do a spectroscopy of a lithium atom, for example, I would like to see if I could actually describe it with an equation like this, and the answer is no, we cannot. Okay, so we have to get better at the description. This is just throwing away too many things. The second approach is assuming a central field approximations. Okay, so this second approach is something that is fairly reasonable. You somehow say, look, now we have many electrons, and I'm going to focus on one electron. In this electron that I will focus, there are some electrons that are living beyond this in a radius further away from the nucleus. So this electron, it's somehow surrounded by a certain amount of charge. That amount of charge that is surrounding, if it is spherically symmetric, won't have any effect on the energy of this electron. Only the charge that is within this inner sphere will have something to do with the energy of that electron. So we're saying somehow that the total energy seen by this electron is the energy, is the total charge seen by this particular electron, the one that I'm trying to show to you. This electron here sees the nucleus, but it doesn't see the nucleus completely because it's surrounded by part of the electron. So the effective charge of that I should put in an equation like this, it shouldn't be C, the total charge of the nucleus inside, but it should be Z minus the electrons that are sort of moving around in a spherical shape around this core, okay? So this is a sort of a reasonable way of thinking. And what you can actually say is that, you know, you can, okay, let's say the potential is actually spherically symmetric. So the potential is not 1 over, you know, 1 over R. It's not C squared 1 over R, but it's some function of R that is spherically symmetric. It's not that I'm seeing the whole number of electrons, the whole number of protons in the nucleus, but I'm seeing an effective charge. And that effective charge that has some sort of spherical distributions produces a potential in a particular electron that I'm trying to describe, okay? So this is the idea. And when you do that and you think it that way with the central field approximation, this is what is called central field because it's fairly symmetric. The phi and the theta equation that we saw back when we saw the hydrogen atom, those equations won't change. So the L and the ML will continue to be reasonable quantum numbers. What it would be different, though, would be the radial equation. The radial equation is the one that gives you the energy at the end. So, and in that end, you have to change the 1 over R potential by this new function, 1 U of R, okay? And so now you get a, you know, out of this, you get another quantum number N, but will be, instead of linked to the Coulomb interaction between point particles, will be something like this U of R will be different, will be a function of R, okay? So we're looking at a different problem like that, but what we know is the L and the M actually make sense because those equations, you separate the variables and treat them, you know, in a different way, yeah. So what we can conclude is that for this atom, the energy will be different to minus 13.6 divided by n squared. Okay, how different? Well, you know, it will depend on how many atoms, how many electrons are actually shading the nucleus. Okay, they are sort of making a screen. There's a screen potential. You know, there's a screen of electrons that actually this outermost electron almost don't see the nucleus. Actually, there are some instances when this electron is so very far, the last electron in an atom is so very far out that you can actually say that the total charge of the nucleus is 1 electron, one positive electronic charge, okay? That will mean that Z minus 1 electron cloud surrounding this thing actually cancel C minus 1 charge of the proton, and only an effective charge of 1 is what is visible. And in some instances, this is a good model to describe it. So this is the type of approximation that we have to do to get to solve this very complicated equation, okay? But that's not all. Well, one of the new things now is that before the energy was only a function of n when we solved the case, and all the L values were degenerate, meaning for a particular value of n, if let's say we are in the second level, we have the possibility of having angular momentum 0 and angular momentum 1. But in the hydrogen atom, without considering the spin-orbit interaction, those two levels are almost the same. Not almost the same, they're exactly the same, okay? Because they are degenerate. But here, despite the fact that we have the spin-orbit coupling that I am not including in this analysis, by the way, you have a dependence of the energy as a function of L. I mean, the energy is not necessarily independent of the value of the total value of the angular momentum. Okay, so because we're solving a different equation now. So in the case of one electron, this is what we had in the hydrogen atom. We had one electron, we have n can be greater than or equal to 1, L can be going from 0 to n minus 1, and the absolute value of ml has to be less or equal to L. Means when we have an L, we have how many components we have? We can go from minus L to plus L in angular momentum, and this thing will be sort of a scale like that. We have ms, which is the magnetic moment of the C component of the intrinsic magnetic moment. The spin component could be plus or minus a half. Okay, so these are the quantum numbers that really one could get in a system. Using this thing, how do you solve this equation? You solve the equation, you find the energy levels, and then you just start putting the electrons in. And what is the ground state for that? The ground state for that will be simply grabbing all the electrons and putting it in the 1s state. That's the minimum energy. So there's no impediment to actually put them all there, and that will minimize the energy. Well, there's a caveat here, and that is that the electrons are peaky subjects, peaky particles. It's like humans when they go in a bus, you know. And usually, let's for this example, it's the same gender bus. Okay, so everybody's the same gender, just to avoid things like particular attractions to some of the individuals. So there are empty seats, and people sit only on empty seats. Okay, because that's the way you want to do this thing. So you have seats in the bus, and somebody get up, and if there's an empty seat, somebody sits there, and you cannot sit on a particular seat that's already somebody there. Okay, and that's exactly what happens with the electrons. And what is an empty seat for an electron? Is a state. A singular state is something that what defines a state are the quantum numbers that you have for it. Okay, so what are the quantum names that we have? Well, we have the n, which is the level of energy. We have the orbital angular momentum, the L. We have the ml. These are good quantum numbers because we know that we have separated both equations. The z component of the angular, that's a good quantum number, and the c component of the spin. Okay, so you can define the L, the ml, and the s and the energy. So you have these four numbers that will make up the quantum numbers associated with a particular electron in an orbit in a position. The exclusion principle, which is what I'm trying to describe you here, is that the electrons don't like to have quantum numbers that are the same. That's the way it works. This has nothing to do with the Coulomb interaction between them, because they have Coulomb interaction and they repel. You know, there are particles that repel, that don't behave this way, and they behave this way because there is a statistical principle that behind this, and it says whenever you put two electrons in a confined system, they should have different quantum numbers, and this is the exclusion principle. This is what makes them particular. Okay. In the language of quantum mechanics, it means that the wave function should be anti-symmetric with respect to the interchange of two particles. What does it mean anti-symmetric? It means that when you change two particles in this global wave function, if the wave function is anti-symmetric, it should change the sign of the particle of the wave function. The change of sign of the wave function is a requirement for electrons. If you cannot change the signs of the wave function by changing two electrons, that is not an electron. Whenever you change the interchange two particles, two electrons that are confined in a system, you should change the sign of the wave function. It is impossible to change the sign of wave functions if two electrons have the same set of quantum numbers. Because if the quantum numbers are the same, you're not going to change anything. Because if you exchange those two particles, the wave function should remain the same. Okay, so this is saying that wave functions of electrons are always antisymmetric with respect to change of particles. That is a requirement for electrons. And that is how the exclusion principle works. And the exclusion, this exclusion principle requires that the electrons must have a completely different set of quantum numbers when combined in a synchronous system. Okay. The particles that obey this principle, this antisymmetric principle, or obey the exclusion, the exclusion principle, are called fermions. Electrons, protons, neutrons, and are all fermions. Those are particles. We have a half integer spin. These guys not only have half integer spin, they are particles that have spin 5/2, for example. Okay. and they are very rare, and they exist by very small times in the universe. You're not going to find spin 5/2 particles sitting around in your desk very easily, but you have to create them in atomic collisions and high energy atomic collisions. Essentially, you can create them, but protons and electrons, and neutrons, they are lying around essentially. And so you can, well, not the neutron, the neutrons need to be close to a proton to actually exist with a big lifetime, otherwise it decays. So solving this problem requires then that to consider this statistical phenomena that the wave functions of the electrons should be antisymmetric. It means you cannot repeat the same set of quantum numbers when actually defining the quantum numbers of a system. Okay. So what does it mean in practical terms? What it means is that if we apply this exclusion principle, we can start. Let's begin with the hydrogen atom. The hydrogen atom has no problem because I can grab the first electron and put it in the lowest energy state, and then there I go to helium. And when I go to helium, I have a C equals to 2. And so I have to put 2 electrons in. I put the first electron in the lowest energy state, which is the 1s state. And the next electron that I put, I have to change something to actually put it in the same low energy state. What do I change? Well, the electron had a spin 1/2. Now I have to flip the spin and put with the spin -1/2. So in the ground states of the helium atom, the spin of the electrons are pointing in opposite direction. Both of them have orbital angular momentum equal to 0. And in addition to that, they have opposing spin. Okay, an opposing spin has 2 options. But we're not going to get into that. Okay, opposing spin can mean total spin equals to 0, or can mean total spin equal to 1. It really, quantum mechanics is funny on this. Okay. So we have this thing that when we have smaller number of electrons, we can populate orbitals that are very close to the nucleus, and as soon as the numbers increase, I have to still start going out. So the electrons cannot be all together bunched in the lowest energy state, but it has to be occupying higher energy state, because otherwise they won't be able to fulfill the exclusion principle. Okay, so how do we do this? Let's think this is the simplest case. This is the hydrogen atom. I put one on there, no problem. This is what we call the K level, the K shell. The K shell is the 1s shell, is the K shell. And this guy will have a J equals 1/2, okay? Then I put down the second electron, and the nucleus also has to increase the charge by 1. So in the case of helium has 2 protons in the nucleus, so the charge is 2e. And now I have to place the 2 electrons in there. So the 2 electrons are placed in here in the same level. And to avoid the thing with the exclusion principle, I just twist the spin of 1, and I get this configuration. Okay. This configuration, as I told you before, could mean having total J equal to 0, total J equals to 1. I don't know if we're going to get to this, but to explain why is this the case. But the actual thing is that the spins should be counteraligned of each of the particles. What happened with lithium? Lithium is assert is Z equals 3, and in the case of lithium, we're stuck, because in the 1s state, I can only put 2 electrons, because the spin, the orbital, the spin angular momentum is 0, and the orbital angular momentum is, the orbital angular momentum is 0. It means that I don't have mLs to change, to put particles in. Okay, I don't have more states, so I only have 2 states. So the L it's a 1s, it's the K shell, and only have that. I don't know what is this. How did that come about? Interesting. So L is the next shell, and the extra electron, the other electron has to go in this shell. It can have the spin either way. I didn't draw it, but it could have the spin either way, you know, up or down. Okay. Okay, and then after lithium, I go to beryllium. And for beryllium, well, I have an empty space here that I could fill with that electron, okay? But in this energy level here, the second level, I still have very close by here, you know, with a slight difference, all these are S level, these are S electrons. I have all the L equal 1 electron, all the P electrons in the second level are still available, and the energy for those are very similar to this one. Okay, if we only include the spin orbit interaction, there will be a small split. Okay, which could be a key. Okay, so we can go on and do this and look at the number of states available for each shell, the K, the L, the M, the N, and so on. Okay, so this is a table here that should explain the whole notation. This is the N equals 1, L equals 0. If L is equal to 0, I have only one chance of using ML. ML should be equal to 0. And the spectroscopic notation of this state is N is equal to 1. That 1 goes there. And since it's an L equal to 0, the L equal to 0 states are called S states. So we have S states here. And the number of states of different quantum numbers that I could hold is only 2 for the spin up, spin down. Okay. If I do that with the second level, well, it's the same as the first one. It's also an S equals 0 state, so I only have 2 states, okay? Then if I go to the P states, 2P states, these are 2P states because the 2 comes from here, the P comes from L being equal to 1, and I have 3 components of the magnetic quantum number of the momentum angular, of the angular momentum of this electron, which can be -1, 0, and 1. And apart from that, I could put the spin angular momentum, which could be adding up or down. So from these 3 states become 6 states when I include the angular momentum, when I include the spin, okay? So this is the way I'm filling the shells now, okay? These numbers here are not exactly, they're not related exactly to the energy as they were in the hydrogen atom, but as soon as the energy increases, this n value increases, it means that the energy is closer to the vacuum level. So we are raising the energy of the electrons, okay? In the n equals 3 level, you can have up to L equals to 2. So if you get all these numbers together, you get here, this is interesting because the number of states here is 2. The number of states here is, if this is 2 states, has to do with n squared, see? Because this is 2 plus 6 is 4 times 2. This is 2 square, this is 3 square. 3 square is 9 times 2 per the electrons give you 18 states, okay? 4 square is 16, okay? 4 is the level. 4 square is 16 times 2, the number of possibilities of that provides the spin of the electrons, give you 32, okay? So this is the way we can, we can hold a lot number of electrons here in this configuration without using the same set of quantum numbers. So this is the important part. And this, for example, would be, I think I did this before. Yeah, I showed this. This is the schematic representation of lithium, where we have the point charge in the nucleus. Then I have 2 electrons in the 1s state, and then I have to go to the 2s state, which is located a bit further away, and I can locate only 1 electron here. So this 1 electron here in this shell has only 1 charge. So I have 1 charge, 1 particle with charge E here, 2 particles with charge E here, and plus 3 particles in there in the nucleus. So this becomes a neutral entity at the end, atoms and neutrons, okay? This is an unhappy, let me try to magnify a bit. So this is the way the electron configurations are labeled, okay? So this is hydrogen. The hydrogen is the ground state configuration of hydrogen is 1s. The ground state configuration of helium is 2s squared. The square that I have here, it means that it's the number of electrons that are in the level s. In the s level is the level with s equal to 0. L equals 0, and the n is equal to 1, okay? Then comes lithium. Lithium has a full 1s state, and the next state goes to a 2s state. Then comes beryllium. Beryllium has full s state, and in the n equal 1, and full s state in n equal 2. It means each one of the states can be 1 or 2. The exponents here can be 1 or 2 in the case of the s states. In the case of the p states here, the s state can only hold 2 electrons per each state. The p states can hold 6 electrons. yeah, because they have the three component of the angular momentum plus the orientation of the spin, which gives you the value up or down. So here I have this could go up to 6, and that's what it does. This is the one. Usually you don't put it, you don't write it up. Okay, only when it's different from 1. When you write 1 without a superscript, you assume that the superscript is 1. If you write a number, well, the number should be different than 1 and should go up to 6. Okay. When you get up to this level here, you're completely a complete second layer. You complete the K layer. The K layer here is absolutely complete. Okay. And this atom here is neon, is actually a very inert particle. Okay. When you form complete layers, these things are very hard to ionize in a way, okay, or to transfer electrons from this guy to a neighboring atom or something like that. So this is something that you have to keep in mind. Then that the properties of the thing start changing in a funny way. Look at I'm gonna go down. Look at this atom here. It has 2 p states here and 2 s states here. Let me go to silicon here. Has 2 s states and 2 p states. So silicon and carbon actually have very similar properties. The difference is the number that is in front of the p states, or where I'm doing it here in the p state. Here has a 3 and here has a 3. Actually, if one builds up a periodic table of this, and this is why it is periodic, is because the properties of these things actually changes. They are not linear with the number of electrons that the thing actually have. So, so what happens is that some properties start to change, and then they go back and start to change again at the beginning. So there is a period. And that's what the name periodic table comes from, that this thing should have similar properties again. And in this way, if one looks at this, one could expect that silicon, which has a 3s, 3p square state, should be very similar to carbon that have a 2s, 2p state. Okay. The only difference is that the outer part of the electronic structure is very similar. It's a bit bigger than the silicon. Is actually a big carbon. You can actually think it that way. Okay, and the inner part plays no role. The inner part, the electrons are there. The only thing that they do, these guys, somehow they screen the charge of the nucleus for the outside electrons, and we're going to see how does that happen. Okay, are we going to see that? I don't know if we can get. Well, this is something you study in chemistry at school, I guess, and there are some rules to actually do this thing, and it has a lot of meaning with respect to how the wave function looks. This is not just letters. Okay. This has to do with angular momentum, and it has to do with a wave function that has a particular shape. And even though we haven't calculated them, we could actually understand them better and infer some of the properties of the material that should be linked to the shape of actually the orbital. So an S and a P should be different, and we will examine some of those things when we get to see molecules, I think. So this is the periodic table. This is how it looks, and I was talking about this. Carbon and silicon are one on top of the other. Here we are completely, the 1s. This is the 2s. I'm sorry. This is the 1s squared. This is the 2s. This is 2s squared. And here comes 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. And here we have 10 electrons. You can count them 1, 2, the number there is 10. You have 10 electrons up to there, and that's a complete layer. And then from here, you go to the next layer down, which is the 3s level. You go to the 3s level, and after the 3s level, you get the 3p level, which goes here, and then you get an exception. Because if one looks at the things in terms of how would they look in the case of the hydrogen atom, one would expect that the 3d levels would be sort of continuing in that direction, but that doesn't happen. The 4s level are actually getting deeper closer to the nucleus. Okay, so they are lower in energy than the D states that are more delocalized. So the shape of the D states compared to the 4s states make the difference in terms of the energy they have. Okay, so the 4s states are closer to the nucleus, and they should be filled first than the D states. So these are the 4s states linked to this. This is 4s1, 4s2, and these are the 3D state. The D states go from 1 to 10. So they are here 1, 2, 3, from 13 to 12. There are 10 states so these are linked to the D states. Okay, so that's how we somehow understand this notation and the disposition in the periodic table. Okay, there are complete courses devoted to this. Okay, almost all chemistry is devoted to this. Okay, so don't expect to understand everything on the first shot, and it should be included in this class. We are gonna pass through this. I'm gonna show you this is it. There's a logic of how you form this thing, and that's what I'm aiming at this moment. I'm not going to do this screening example because it's going to be, I'm going to leave it midway. I want to somehow understand how the screening effect works. The screening effect is that the inner core electrons actually somehow screen the charge seen by the outermost electron. Okay, and we're going to see an example here and what are the implications for that. And I'm going to leave this example for the next class. I don't want to run through this thing in the last 3-4 minutes that's still left. So guys, this is the class for today. I don't know if you have any questions. We have time for a few questions if you like. If you have any outstanding requests.
Particularly, to be honest, at least from my case.
Okay, guys. As usual, there's a lot to read, and this is not very cumbersome. There's a lot to read because there are not many equations to solve, but there's a lot of information to be acquired. Okay, because I'm actually telling you what the solutions of the equation are, and that tail is actually sort of like history somehow, and you should learn there are some things that are valid and some things that are not, and they are based on solid mathematical grounds that we're not getting through all the details here. Okay, so that's part of the subject. And we're going to keep looking at this and end up with this discussion. We are going to go next time to see something that has to do with quantum mechanical effects on two systems of qubits, which is something that might interest some of you in terms of information theory, because the next computers are not going to be silicon-based, they're going to be quantum mechanical computers. Okay, so we're going to see if we can trace a few things of that subject in the next class. Okay, so this is it for now. enjoy the weekend, guys. Thank you for the Thanksgiving and have a lot of fun tonight. Okay.
Have a great day, teacher.
Yeah.
See you next
Ciao,
week.
ciao.
See you next week.